Hey everyone, welcome back to MLworks. In this video, we'll understand the concept of speculative decoding, which will help you to improve the performance of LLM inference. So this is purely a theoretical video where we understand what is speculative decoding and what are the different types of algorithms that are being used to ensure your LLM inference is faster. Okay, so for the implementation aspect, I would recommend watching or even look into the library of VLLM where speculative decoding is implemented. So before we get started with what is speculative decoding is, let's understand the challenges of current LLMs. So all the latest LLMs that are getting deployed, okay, or being developed are larger in size. By that I mean they have billions of parameters. Okay, when you try to give an input token to generate the next token, it has to go through all these billions of parameters to generate the next token. Okay, and if you have to generate for a paragraph or a document, okay, it takes a lot of time, okay, to generate the whole document because it has to go through all these parameters and then it has to generate the final output. Okay, one text generation, right? One token at a time. Okay, so that makes the whole thing very expensive to generate and makes the whole inference very slow. And when it comes to applications like chatbot or real-time translation, so this slow inference is not very useful and it kind of makes the user experience poor. Okay, so let's understand what is speculative decoding and how it can help you to reduce the time taken for doing an inference through LLM. Okay, the whole idea is to reduce the inference time significantly when you're doing the inference. So in general, okay, when you're trying to do inference through LLMs, okay, it has to generate one token at a time, and the output token is again taken as an input and then generate the next set of tokens. So the idea here is to parallelly generate the multiple tokens out and then use some larger model to understand whether this token was correct or not, and if it is not correct then discard it and do the same. Okay, so in parallel you will be generating multiple tokens instead of single token, right? So that's what the whole idea is. So on the right hand side we can see the concept being implemented with and without speculative decoding, and with speculative decoding we can see the time taken to generate the tokens is quite less compared to without speculative decoding. Okay, so let's understand the basic token generation process, right? So generally LLMs token generate tokens one at a time, and a token is nothing but a word or as a part of a word. And normally, okay, these tokens are nothing but when you there are tokenizers. Okay, when you give an input sentence, it will be turned into tokens. Okay, for example, in this sentence, okay, one small step for man, one giant leap for mankind is passed to a tokenizer from, you can consider any of the tokenizers, right? And it gives you 12 tokens. Now, to generate such a sentence through a large language model, okay, the LLM has to run 12 decoding steps. Okay, so it has to read all the data for every token generation, which makes it very, very slow during the inference aspect. Okay, and typically LLMs generate many words, okay, such as for the conversational response or the summary of a document. And since each token output depends on the previously generated token, okay, it has to read all the model weights again and again. Okay, so that is one of the key concept, right, which makes the whole inference process slow. So there are two key observations that had motivated the speculative decoding method. Okay, let's understand those two key observations. So first is some tokens are easier to generate than others. That is the first observation. And the second observation is the bottleneck for LLM is the memory. Okay, so let's understand what is the observation one it talks about. So consider you are giving an input like what is the square root of 7, and the LLM generates the square root of 7 is 2.646. Now the tokens like these, the square root of 7, it's quite easier to generate given an input like this. Okay, and the token 2.646, it's quite hard to generate because it has to do some kind of manipulation in the backend and then come up with this specific token. Okay, so there are two parts. Okay, one is a tough token, that is a simple tokens. So simple tokens, okay, can be generated by smaller models also, and the tough tokens requires larger model. Okay, so that idea of some tokens are easier to generate and some tokens are tough to generate gives you the idea of having two models. One is larger model for tougher tokens and a simpler model for simple tokens. And when it comes to the second observation, that is bottleneck for LLM inference is usually memory. So normally we run a large language model on GPUs or TPUs. Okay, and these hardware systems are capable of performing trillions of operations per second. But when we are using this for transformer-based large language model, they don't efficiently utilize these memory, okay, or these operations per second efficiently. So for instance, the hardware is capable of doing hundreds to thousands of operations per byte rate, okay, but the transformer architecture only makes use of around 10 operations per byte rate, okay. So there are like 1/10 or 1/100th of the operations that are being not utilized. So there is some memory resources that is available to you that you can utilize, and there is two models that you can use for generating the tokens. Just understand these two observations and how these will help you to reduce the inference time. Okay. So first concept is speculative execution. Okay. So when we talk about computing resources that is available for you to utilize, okay, what you can do is you can parallelly execute kind of a decoding process. Okay, as I said earlier, there are like 12 decoding steps happen to generate a 12 tokens sentence. Okay, what you can do is you can parallelly try to generate multiple tokens at a time and efficiently utilize the memory that is available with the GPU or TPU. So then idea becomes which tokens, right? In this case, okay, to perform speculative execution effectively, we need to have an effective mechanism that can suggest tasks that are likely to be needed. So in this case, the task is nothing but the token that is needed, future token that is needed. Okay, so we have to identify such tokens effectively. So this whole concept of speculative execution comes from an old concept, which is speculative execution, named as speculative execution. It is an optimization technique where a task is performed before or in parallel with the process of verifying whether it is actually needed, resulting in increased concurrency. So a task is performed, a task is predicted, okay, in parallel, okay, whether that task will be needed or not, or whether this task will be useful or not, okay. So if it is useful, then you have managed to increase the concurrency. If you have not, then you just discard the results that you got. So this is one of the key concepts which is being used in modern CPU pipeline, okay, for branch prediction. So I would recommend reading this concept to understand speculative execution. So the mathematical concepts right here. So consider you have two complex lengthy functions, f of x and g of y. These two are same functions, but it takes time to get the results. Okay, what will happen, right? When you are having a function like these, f of x gives y and g of y gives z. Without speculative execution, what will happen is the output of this, okay, and this is g depends on output of f of x. Okay, so it has to go through sequentially. Once y is generated, then only z can be generated. So that's how the sequential operation will happen without speculative execution. But with speculative execution, what you do is you create an approximate function of f of x, which is f star of x. Okay, then you simultaneously try to run both the function and get the output. Okay, once you get the output, you check, okay, whether y is equal to f star of x, the output generated by the f star of x. If both are equal, so we manage to increase the parallelization. Otherwise, we just discard the value generated by f star of x. Okay. Otherwise, that's what we discard the value of f star of x and then go back to calculating g of y, which is already generated. Okay. So this effective mechanism, right? Okay, what it will do is it will try to increase the increase the concurrency. Okay, and it also the output that we get, it is guaranteed to have the identical outputs either way. So that's the key idea. You are trying to parallelly run for f of x, one through f of x and other through f star of x, which is an approximation of f of x. Okay, you are trying to do it parallelly and try to reduce the inference time, okay, in terms of LLM. Now, this f star of x, we just talked about f star of x, okay, the approximate function of f of x. Now, how to select f star of x? So, this is done by speculative sampling, which is nothing but a technique of generating in terms of LLM. It's a technique of generating the text using a draft model. Okay, a smaller, faster model to predict the new next few tokens. So here f of x is nothing but your parallel tokens that you generate. That is what f of x is, f star of x is. Okay. So for that, what we do is use something called a speculative sampling, which is nothing but a draft model, a smaller and faster model for generating the next set of tokens. So if you just look at this diagram, you have initial prompt. So you use draft tokens generated by the draft model, and you verify those draft tokens through a larger model. If it is good, verification is passed, then it's good. You can go ahead and use it. If it is failed, then you have to regenerate the text and get it final verified text. So the final step, f star of x is our draft model trying to replicate the results of f of x. Okay, and that's what we have understood from speculative sampling. So speculative decoding is nothing but an application of speculative sampling. Okay, so it is a way of generating output tokens parallelly. Okay, such that those tokens are tokens are generated fast and quickly, and you don't have to wait for the larger model to generate those tokens. Okay, because larger models takes time. Okay, so you use a draft model which will be quick and generate those tokens which are easier to generate, and that's the key observation. For example, right, this is observation 1 which we saw earlier, suggests that smaller model might do well on the easier tokens. So for example, okay, when applying speculative decoding to accelerate an 11 billion parameter T5XXL model for translation task and using a smaller 60 million parameter T5 small as the guessing mechanism. So there is this larger model of 11 billion parameters, okay, which will generate the tokens. But for the easier tokens, what you do is you use smaller 60 million parameter T5 small model, okay, which will generate easier tokens for you. And this will result in reduced time for doing the inference overall. So if you see here, we get 3x improvement in its speed for generating the translation task, right? For the translation task, the speed is increased by 3x when you are using smaller 60 million parameter T5 small model. So let's understand. So here we have, without speculative decoding, we have one large language model which will generate one token at a time. But with speculative decoding, you have a draft model and there is large model. So small model will try to generate the set of tokens, and the large model will try to verify whether the token generated is good or not. So if it is not good, it will redo the same set of tasks and generate the token, which I'll show it here again. So if you see, if you see the time taken for generating the sentence, okay, it's taking a lot of time without speculative decoding. So if you see here, there is something red color it getting generated. Okay, it gets again restarted. Okay, so whenever it is not able to guess properly the smaller model, the larger language model will try to regenerate the text. Okay, so that's the key idea behind speculative decoding. So what are the application and challenges of speculative decoding? Application is especially it is used for virtual assistants and chatbots where you need real-time output from the large language model. If you want to do real-time translation, then you need some concepts like speculative decoding, which reduces the time taken for inference. For content generation and gaming and interactive applications, we can use speculative decoding. But the challenges with speculative decoding is you have to manage the model states for the draft model and the large language model. And how you select your draft model, it's also one of the challenge. And managing these two models is also increases the complexity. And the large language model has also the overhead of verification. So it has to verify the output generated by the smaller model is correct or not. So these are some of the challenges with speculative decoding is. So these are some of the reference material for understanding what is speculative decoding. I recommend reading through all this 4 different blog posts or paper. Okay, so this is very good for understanding how speculative decoding works. So with that, I'll conclude this video. Thank you for watching.